Hello everyone and welcome. So today we're jumping into a chapter that I know gives a lot of you some trouble. Organic chemistry. But listen, don't you worry. We're going to make this super simple. We're talking about haloalkanes and haloarenes. And I promise, by the end of this, you'll feel so much more confident. Let's get right into it. Does this sound like you? I hear this all the time. It's the #1 fear students have. Sir, my 11th grade concepts are not clear. How will I ever understand this? Well, I'm telling you right now, forget that fear. We are going to start from scratch. Bilkul basics say. This is for everyone, especially if you're feeling a little lost.
Okay, so first things first. Let's meet the two heroes of our story today, haloalkanes and haloarenes. Think of them as two brothers from the same family, the hydrocarbon family. They are very similar, but one tiny difference in their structure changes everything about them.
Let's talk about the first one, the haloalkane. It's really simple. You take a normal alkane, a simple chain of carbons and hydrogens. Now imagine a halogen atom comes along. Halogens are your fluorine, chlorine, bromine, iodine. We often just call them X to keep it simple. This halogen just kicks out one hydrogen and takes its place. It's like it gives the carbon chain a big hug. That's it. You have a haloalkane. Now for the second one, the haloarene. This one's a little bit of a VIP. Why? Because it involves the famous benzene ring. Here, the halogen atom doesn't attach to any simple chain. No. It attaches directly onto that special, stable, aromatic ring. You can just picture the halogen chillin' on that benzene ring. And this small fact, my friends, is a total game changer.
So why is it a game changer? It all comes down to this. In a haloalkane, the carbon holding the halogen is sp3 hybridized. Think of it like a camera tripod with its legs spread out. It forms a simple, straightforward single bond. But in a haloarene, that carbon is part of the flat benzene ring, so it's sp2 hybridized. And because of this, the electrons in the ring are shared all around. We call this resonance. This sharing gives the carbon-halogen bond some double bond muscle. And what's the bottom line? A stronger, shorter bond that is much, much tougher to break.
All right, so we know who they are. But you know scientists, right? We love putting things in boxes. We love to classify. So let's see how we sort this big family into smaller groups. It's actually very logical and easy to understand. Look, it's a simple 3-step game. First, you find your target, the carbon that's holding the halogen. Got it? Okay, step 2, just look at that carbon and count how many other carbon friends it's directly holding hands with. If it's holding hands with one other carbon, we call it primary. If it's holding hands with 2, it's secondary. And with 3, you've got yourself a tertiary haloalkane. And you have to pay attention to this, because this little detail, primary, secondary, or tertiary, is going to decide its entire future, how it's going to react. So we've met them, we've sorted them. Now for the really cool part. Let's talk about their origin story. How are these molecules even born? How do we make them in a lab? There are a few key recipes or methods that you absolutely need to know. One of the most famous rules in all of organic chemistry is this one, Markovnikov's rule. And the way to remember it is perfect. The rich get richer. Imagine an alkene with its double bond. When you add something like hydrogen bromide, the hydrogen atom is choosy. It will always go to the carbon atom that already has more hydrogen atoms. Just like in life, right? The rich get richer. It's an easy way to predict the outcome. Now let's talk about some special named reactions. First up, the Finkelstein reaction. This is our go-to trick if we want to make an alkyl iodide. And the clue is right there in the name. Finkelstein. See that I? It's practically screaming iodine at you. We use sodium iodide, NaI, to make our alkyl iodides. See? Finkelstein, NaI, iodide. It's a perfect match. And what if we want to make fluorides? For that, we've got the Schwarz reaction. And I have a great trick for this one. Just think swag. Seriously, the S and W are for Schwarz, and the Ag is for silver, Ag, as in silver fluoride, AgF. So Schwarz means you need some swag, some AgF to make your fluorides. It's a silly trick, but I promise you, you won't forget it. Okay, we know how to make them. Now we get to the real drama, the personality test. What are these molecules really like? How do they behave when they meet other molecules? This is where we see their true colors, their signature reactions. So there are 2 main personalities, SN1 and SN2. Think of SN1 as a 2-step drama. First, the halogen leaves. Just poof, gone. This creates a carbocation. And who is best at handling this? The tertiary carbons. They are the most stable. Then the new group can attack from the front or the back. Now, SN2 is different. It's a one-step coordinated dance. The new group attacks from the back at the exact same time the old halogen is leaving from the front. It's a sneaky backside attack, and for that, you need space. That's why it works best for primary haloalkanes, where there's less crowding. These two mechanisms are polar opposites, and they are so, so important. So, we've gone through all this theory. I can almost hear you thinking, "Sir, this is great, but so what? Why does this even matter outside of my chemistry class?" Well, let me show you. It turns out these molecules are hiding in plain sight, all around us. Just look at this list. That paint remover you have in the garage, dichloromethane. The air conditioner that's keeping you cool, it used to run on freons. The deodorant or hairspray can you used this morning. Yep, haloalkanes are used as propellants. They've been used in fire extinguishers, as anesthetics like chloroform in the old days, and even as powerful insecticides like DDT. Now, of course, some of these have been phased out because we found out they were bad for the environment, but it just goes to show you how important and widespread this family of chemicals really is. So you see, understanding haloalkenes and haloarenes, it's not about memorizing a bunch of random facts and rules. It's about learning a story of how a molecule is built, how it's made, and how it behaves. At the end of the day, that's all organic chemistry is. It's the story of molecules. And we've just uncovered one chapter together. The only real question left is, what story will you uncover next?